Okay, good day to each and every one of you. This will be a second problem or example for the shear and bending moment diagrams. And let's try to simplify this kind of problem to the simplest form so that we don't have any information overload, and that will be inefficient for us to somewhat understand the concept and the meaning behind shear and moment diagrams. So in solving shear moment diagrams, since we have this flat beam over here and supported by two types of supports, we have the pin at point B and we have a roller at point C. Okay. And the first thing that we must do in solving these kinds of problems, and our supposedly goal here is to graph the shear moment diagrams, is we must try to solve first the reactions for both supports. That's why it's called a structure, because it has supports. And the first thing that we must do here is to apply the available formulas in the laws of equilibrium. That would be the summation of forces along the y-axis, along the x-axis, and the summation of moments. So let's start by solving first the reactions for both A and C, corresponding for the pin at B and then for the roller at C. So let's try to solve it here on this portion of the whiteboard. If this is the free body diagram of the whole beam, and we have a roller at this portion, this is the reaction at C, and here somewhere this would be reaction of the pin B going up, and obviously we have this what you call uniformly distributed load acting downward, and this 200 pound load at point A. So this is A, this is B, and this is C. So our goal is to simply solve for both R sub B and R sub C. But since we have this uniformly distributed load, we must first look for the concentrated load of this distributed load. And how are we going to do that? Since this is a uniformly distributed load and it has a geometrical shape of a rectangle, then we just need to use the formula for determining the area of a rectangle. And don't forget that this uniformly distributed load has a value of 120 pound per foot. 120 pound per foot means to say that for every 1 foot it has an equivalent force of 120 pounds, and then it spans to 10 feet. Okay, so this one is 10 and this one is 4. Okay, corresponds to the length. Let's try to solve for the concentrated load of this uniformly distributed load. So that should be let's designate that as P sub C is equals to, what is the formula of the rectangle? That is simply length multiplied by the width. So the length would be 10. Okay, that would be 10. So that would be 10 multiplied by its width, or let's say height, length times height. That should be 120. Okay, 120 pound foot. And don't forget that the unit for 10 is in feet, so you can just simply cancel out this feet. Okay, and the answer for that one, P sub C, is equivalent to 1,200 pounds. So, and the question here is, sir, where can we find that 1,200 pounds? Well, the answer for that question is, if this is the rectangle, it has a length equivalent to 10 feet. Obviously, the centroid of the rectangle is only half of its length, L over 2. If this is 10 feet, then approximately here at the centroid, that is where 1,200 pounds can be found. Okay, so let's try to get the centroid of this one. Let's assume that this is C sub rec, which is simply half of the length. So that should be 5 feet. Okay, that's the centroid. And let's go back to our initial free body diagram. if this is the beam, so this one is 4 feet, this one is R sub B, and this one going up is R sub C, and the length of this one is 10 feet. We have here at 5 feet measurement going down, because this is our concentrated load, 1200. So 1200 pounds, and we have here at the edge of point A, this is point A and this is point C, that is 200 pounds. So now we can simply use the summation of moments from this step. So let's apply the summation of moments, and if you want, you can start here at point B, or you can start here at point C. It depends on you where you are convenient, okay, where you are comfortable. But for me, I'm going to use the summation of moments at point B. So rotating clockwise is positive. The summation of moments at point B is equals to 0. So all forces along the B pivot point should be equals to 0. And the whole structure, if we add all of those moments, it should be equals to 0, so that our structure is static. That's why it's summation of moments at B equals to 0. So let's just simplify. We have this R sub C going to rotate counterclockwise, so that should be negative R sub C multiplied by its perpendicular distance, 10 feet, and we have this 1200 pounds going to rotate clockwise, so that should be positive 1200 pounds multiplied by the perpendicular distance should be 5 feet, okay, because it's half of the length of this rectangle. And what else? We have this 200 going to rotate counterclockwise, so that should be negative 200 pounds multiplied by the perpendicular distance equivalent to 4 feet. Solving for R sub C. So R sub C is basically all of this divided by 10 feet. And the answer for that one should be 520 pounds going up. So this is the reaction for R sub C. And the next one is just, we can use the summation of forces going up is positive along the y axis equals to 0. This one is just basic algebra. Then dividing by 10 after you transpose R sub C to the left, then divide by 10. So that should be, all of this should be equal to 5,200 pounds. And divided by 10, so that should be 520. Okay, so let's try to solve for R sub B. So sum all of the forces acting on the vertical, so that should be negative 200 pounds. We have this negative 1,200 pounds. We have this R sub C, which is 520, so positive 520 pounds. And last but not least, plus R sub B. All we need to do is to solve for R sub B by transposing everything here to the other side and then rearrange. So R sub B is equals to 1,200 pounds plus 200 pounds minus 520 pounds. So the value for the reaction at B is equals to 880 pounds going upward. So we managed to solve for the reactions for our given beam. And the next thing that we must do here, since we managed to solve the reactions, don't forget about this information. We need that for our later solutions. Since our beam has 3 points A, B, and C, then for this case we must do the method of sections twice, here between A to B and then B to C. Okay, so upon doing that, I'm just going to free some space here in our whiteboard so that we can solve the next step for this problem. Don't forget about the values for the reactions. That is important for solving our given problem. So out of the way. So the next step is to do the method of sections between sections A to B and then B to C. Okay, so we're going to do the method of section at this point. So let's say this is section 1-1 and this one 2-2. Okay, so we have two segments for this problem. We're going to consider first the left side of any given segments. Okay, if you want, you can start here on the right, or if you want, you can start on the left. Depends on you. But for me, I'm going to start on the left side because it is much easier, and that is the conventional way in solving these kinds of problems. So let's draw the free body diagram for segment A to B. It goes like this. This is segment A to B. We have here 200 pounds going downward. We have here the shear load V and the bending moment M. Depends on you if this is the portion of the beam where we managed to do the section. It depends on you if you want to designate that as point E, or if you want it to be X, or you want Y, Z. Depends on you where you are convenient. So since we don't know what is the exact length of this section of the beam where we managed to cut, we can just simply designate that as an indefinite measurement equivalent to X, because we don't know what is the exact value of X, so we can only approximate. Okay, so solving for this one, all we need to do is to solve first for the shear load and this bending moment M. So upon doing that, all we need to do is to use the summation of forces along the vertical in order for us to solve for V. Okay, so upon doing that, that should be the summation of forces going up along the y-axis is equals to 0. So we have this negative 200 pounds. We have this negative V, and there are no more other forces acting along the vertical axis. So we can just simply solve for V by transposing it on the other side of the equation. So V is equals to negative 200 pounds. Means to say, if we have this negative value, then we can just simply change the direction of this vector representation for the shear load. But for me, I'm just going to let it slide for now so that I won't get confused in our later computations. So we managed to solve for the shear load here at section A-B. Okay, don't forget about that. This is segment A-B. The shear load is equivalent to 200 pounds going downward. And the next one is to solve for the bending moment. So I'm going to do here is to use the summation of moments rotating counterclockwise is positive at point E where we do the sectioning. So B is E, this is E, is equals to 0. Okay. So looking for all the forces that tends to rotate our structure. So we have this 200, okay, 200, so that should be positive 200 pounds. And then the rotation is counterclockwise, so that's why it's negative, and the perpendicular distance equivalent to X. And we have this positive bending moment at point E. Okay. So solving for M sub E, so that should be simply transposing this 200 pounds X to the other side. So M sub E is equals to negative 200 X, and then the unit pounds, then foot, because the unit of this X is simply in feet. So we're going to continue this in the part 2 of this discussion.